Putting all these surveys together, we find that society's attitude towards an individual's involuntary fatality risk, if it is 10 to the minus 3 per year, it is clearly unacceptable. On the other end, if it's 10 to the minus 6 per year or less, then it's acceptable, it's okay. And in between these two limits, 10 to the minus 4 per year seems to be tolerable, but barely so. We would like it to be less. Now, with these in mind, we find that the general consensus that have developed around the world for acceptable risk of an individual fatality for a member of the public from building collapse should not be more than 10 to the minus 5 per year, and if possible should be closer to 10 to the minus 6 per year. So that's what we find the acceptable standards now. If you want more information, I would refer you to these two papers. Now, continuing with our earlier thought that building failure or a structural failure does not necessarily lead to one potential fatality, there could be multiple fatalities. So it's instructive to see how investigators and agencies have handled that possibility. One of the earliest examples that we see in setting allowable annual target failure probabilities for structures came out of the UK in 1977, the CIRIA report. It's instructive to see, let's this equation and go term by term. So the allowable PF is the product of three numbers. So there is P prime, which is the base rate, and it's 10 to the minus 4 per year, as we just discussed. Now, this base rate can be adjusted by two numbers, and one is KS in the numerator, and NR is number of people at risk, so number of potential lives lost. So clearly, what CIRIA felt that it's just proportional. If more number of lives are lost, then the single individual's fatality risk should be reduced exactly in that proportion. Now, this number KS, it depends on what sort of structures we have and whether the risk is voluntary or not. So if it's an offshore structure, for example, it's quite likely that the person on board the offshore structure is a professional and has done so fully knowing the risk. So then the allowable PF can be multiplied by a factor of 5. On the other hand, if it's a place of public assembly, it's member of public for whom the risk would be involuntary. So then that number can be brought down by a factor of 0.005. So in effect, we would have something like of the order of 10 to the minus 6 or less would be the allowable PF. So this way we see how a very early example tried to handle the possibility of multiple fatalities. A few years later, we find another example coming out. This is the reference of the Syria report. The next example came out of Canada, and this is a paper by Allen. And this is interesting. It has a different logic. The P prime quantity is still there, but there are three factors now multiplying P prime. And the first thing we notice is the presence of square root of NR. So here the allowable risk is not going down proportionately with number of lives lost, but with the square root. So it's kind of this model is insensitive to a larger number of deaths in one accident. The other, this P prime is 10 to the minus 5 per year. That's the base acceptable probability. But then we can see the different multipliers, A in the numerator and W in the denominator. So let's take a look at A first. So if it's normal activity, then we don't change P prime. If it's high exposure, so again, if it's construction work or offshore work, then it can be even increased by a factor of 10. For bridges, it's something between normal activity and high exposure. So A takes care of the activity, which in some sense looks at the voluntary or involuntary nature of the exposure. The warning factor, W in the denominator, that would be 1 if there is no warning at all. So it's complete sudden failure. And we have seen these earlier when we were discussing all the design standards who are putting acceptable PFs depending on consequence of failure. So if the failure is gradual or if complete fail-safe condition, then the PF can actually be increased. So W can be less than 1. So it could be even 10 times more if there is adequate warning. So that's the sort of suggestion that came out of Allen's work. Almost 2 decades later, let's go on to one example, and this is now an international standard, the ISO 2394 of 1998. So let's read some of the texts from the standard carefully. So clearly, the 1998 edition of the standard says that 10 to the minus 4 per year of an individual's risk of death is acceptable, and then 10 to the minus 6, based on that, 10 to the minus 6 would be that from structure. So that would be the limit they would like to put from failure of building structures. So expressing the failure as the product of one conditional is the death from structural failure is probability of death given structural failure times the structure fails, the probability that the structure fails. It should not be more than 10 to the minus 6 per year, as they just stated, and then the structural failure probability should be limited to 10 to the minus 6 per year divided by the probability of death given the structure has failed. Now that could be, obviously the worst case would be 1, so we would have 10 to the minus 6 or somewhat higher if the failure of the structure does not necessarily lead to an occupant's death. Let's compare some of the numbers now with what we observe in terms of building collapse frequency. Actually, we have some estimates. This number is from Ellingwood's paper, the one that I just referred 2 or 3 slides back. So most published estimates of building collapse would be found are found to be less than 10 to the minus 5 per year in the US. In India, I have found that for engineering buildings in metros, the rate is a little higher. It's between 1 to 5 times 10 to the minus 5 per year. So that's what we have found from recent building collapses around the country. So that gives an idea about what the structural failure should be according to ISO 2394/1998 and what we typically observe around the world. Now, let's see how ISO 2394 handled the possibility of multiple fatalities. So this statement is instructive, that where a large number of people may be killed, in that case the authorities would like to avoid such accidents. And then the requirement that ISO 2394 of 1998 suggests is that it should be proportional to 1 by NR squared in the denominator. So if more number of people would be killed, PF should be reduced disproportionately. So more emphasis is given on the number of lives lost in a single event, not proportional, but NR to the power of 2. And then we see that so alpha is 2 in the denominator, which is the exponent of NR. And then that A value could be 0.01 or 0.1. Those are just examples, but it shows that PF would be further reduced. So that would be the factor which we are going to use to set PF. Interestingly, an economic based analysis in the next revision of 2394 actually changes that approach of alpha of 2 and brings back alpha to about to 1, and that's what we'll see later in this lecture. Putting all of this together, it seems that for multiple fatalities, or with the possibility of multiple fatalities, PF should be less than the number of lives at risk to the power of minus alpha, and alpha, depending on the investigator and the agency and their priorities, could be 1, could be less than 1, could be more than 1. And then there are factors which could increase this acceptable probability of failure if there are risk mitigating factors, or they could further decrease this if there are risk aggravating factors. And then multiplying that is always the maximum acceptable failure probability, which could be of the order of 10 to the minus 4 per year or such, depending on society's attitude towards such risks.